All right, so we know a computer sees a grayscale image as just a big grid of numbers, right? A matrix, where every number is just a pixel's brightness. But that opens up a whole new puzzle.
So if one number handles black and white, how in the world does a computer capture, the entire rainbow? How many numbers does it take for just one colored pixel? That's the big question we're going to dig into today.
Well, right off the bat, it's pretty obvious that one number just isn't going to cut it. Color is way more complicated than just brightness. I mean, think about it. You could have a bright red pixel right next to a bright green one. They could have the exact same brightness, but they're totally different colors. So yeah, a single number? No way.
So what's the trick here? How do our phones, our cameras, all this tech capture the vibrant world we see and, turn it into something a computer can actually process? The solution is both really clever and honestly, surprisingly simple. And here it is. It's called the RGB solution. And it's brilliant. Instead of trying to cram everything into one number, the system uses 3 separate numbers for every single pixel. One for red, one for green, and one for blue.
That's right. Every single color you are looking at on your screen right now is just a specific recipe, a mix of different amounts of red, green, and blue light. This little triplet, RGB, it's the fundamental building block of all digital color.
So let's make this real. Say you want pure red. Well, you just crank the red value all the way up, in this case to 255, and you turn the green and blue values all the way down to 0. Boom, pure red. It's that simple.
And as you'd expect, this pattern just keeps going. Want pure green? You already know the answer, right? Set red and blue to 0 and just max out that green value.
And of course, to round out our primary colors, pure blue follows the exact same logic. Red and green are off, blue is cranked all the way up. The key thing to get here is that each color gets its own dedicated intensity dial.
Okay, so what about the extremes? What happens if you turn all 3 colors off? You get 0, 0, 0, which is black, right? The total absence of light. And if you do the opposite and turn them all on full blast, 255, 255, 255, all that light combines to create pure white. Okay, so every pixel gets 3 numbers. Simple enough. But this is where we get to the really cool part, the secret sauce, the thing that unlocks how computers actually deal with all this data. It's an idea that a lot of people miss when they're first starting out. Now, you'd probably assume that a color image is just one giant grid, and inside each little box in that grid, you've got your RGB triplet. I mean, it seems logical, right? But that's not actually how it works. The real way is so much more elegant.
Here's the big reveal. A color image is actually 3 completely separate matrices, all layered on top of each other. Think about it. There's one entire grid just for the red values. Then there's a second grid layered on top just for the green values. And finally, a third one on top of that for all the blue values. You stack them up, and that's what creates the full color image we see.
But why? Why go to all that trouble of keeping them separate? Well, it turns out this triple matrix design is exactly what makes digital images so incredibly powerful and flexible for a computer to handle.
Because those color channels are separate, you can do some amazing stuff. You can, say, boost all the reds in a photo without touching the blues or greens at all. Or you could literally just remove the entire blue channel to see what the image looks like without it. At the end of the day, it keeps things really clean and simple. For a computer, a color image is still just numbers in a grid. It's just 3 grids now. And that means it's still super friendly to do math on.
So we've got this incredible, flexible system for dealing with color, which leads us to a pretty weird paradox. If all this color information is so rich and useful, why do so many computer vision algorithms start by just throwing it all away and converting the image right back to grayscale?
It all boils down to a really simple trade-off. See, a color image has literally 3 times the amount of data as a grayscale one. That means more space to store it, and more importantly, way more processing power needed to work with it. For a lot of tasks, like finding the edges of an object or recognizing a shape, all that extra color info, it's just not necessary. All that matters are the changes in brightness. So, for the sake of speed and efficiency, color often gets left behind.
So, let's wrap this up with a big idea to remember. A digital color image. It's not magic. It's not like mixing paint. At its very core, it's just data. It's 3 simple grids of numbers, all working together in harmony to show us the world.
And really getting that, that's the key to everything that comes next. Now that you know the secret of the triple matrix, what do you think happens when we start messing with those numbers on purpose, when we start doing math on those pixels? Well, that's exactly what we're going to dive into next time.